Welcome to the steam distillation video. In this video, I'll be going over the definition of steam distillation. I will show a diagram of the steam distillation apparatus, and then we'll go into lab and do the complete experiment. Here is a high-level overview of the definition of distillation. It's a separations technique that allows for the separation of components according to their boiling points. Steam distillation allows us to isolate an organic oil at around the boiling point of water, so this is really useful since many organic oils have a much higher boiling point than water. Here is a simple diagram of the apparatus we will be using. We'll begin with water and cinnamon in a flask. We'll heat it up, steam will rise, and then we'll cool it down using a water condenser. The solution that condenses is called a distillate. It contains a cinnamaldehyde and water. This is what we'll be collecting. Like I mentioned in the previous slide, cinnamaldehyde has a very high boiling point. Water has a much lower boiling point. Since these two compounds are immiscible, we're able to use steam distillation and heat this up at around the boiling point of water instead of the boiling point of cinnamaldehyde. Let's go to lab. A 50 milliliter Erlenmeyer flask containing a spin bar is topped with a Hickman still. A water condenser is placed on the top of the still, water coming in through here and water coming out here. We'll begin by adding 10 to 15 milliliters of water to the flask. Then we'll add 10 drops of Triton X45, which is a surfactant that will break up the surface tension between the cinnamon and water. We'll add the 10 drops using a pasture pipette. Remember to discard your pasture pipette in a glass-only container. 2 grams of cinnamon is added last to prevent it from burning to the bottom of the flask. Record the amount of cinnamon that will be used. You can place a weighboat on the scale, tare it, and then add the cinnamon on top. You are not expected to weigh exactly 2 grams. Carefully add the cinnamon to the flask. Now we will place the Hickman still and water condenser back to the top of the Erlenmeyer flask. Carefully begin heating the flask and stir vigorously. At this point, we want to turn on the water source of the water condenser. Carefully monitor the heating of the flask. Heating the cinnamon slurry too much will cause it to boil over, and not heating it enough will prevent you from collecting distillate. You'll want to be prepared to fan the Erlenmeyer flask or raise the glassware off of the hot plate if the boiling becomes too aggressive. Since we'll need to collect about 5 to 7 milliliters of distillate in a large test tube, we can measure this amount by adding about 7 milliliters of water into a clean test tube and marking it up with a Sharpie. Then we can empty out the water from this test tube and begin collecting distillate. After 5 or 10 minutes of heating, you should begin to notice condensation occurring. If there is no condensation occurring, then you should increase the temperature of the hot plate. After a few more minutes, the collar of the Hickman still will fill up with distillate and can be removed using a pasture pipette. Begin by removing the cap of the Hickman still. Then, using a pasture pipette, remove the distillate from the collar of the Hickman still and place it in a large test tube. Be sure to replace the cap on the Hickman still. You will repeat this procedure multiple times until you have collected about 5 to 7 milliliters of distillate. This may take up to 1 hour. Remember to maintain proper control of the heat so that the slurry does not reach the neck of the Erlenmeyer flask. Okay, so now we have collected a little less than 7 milliliters of distillate. Before we begin extraction, it is important to clean the cinnamon from the reaction flask as soon as possible. We'll begin by lifting the apparatus above the hot plate and letting it cool down for a few minutes. Then we'll remove the water condenser and the Hickman still. To remove the burnt cinnamon, we add 15 milliliters of water and 1 gram of sodium bicarbonate to the flask, and then heat gently while we perform the extractions. We'll extract our distillate 3 times using 2 milliliter portions of methylene chloride. I have placed a sufficient amount of methylene chloride in a small beaker and will be doing the extractions using a pasture pipette. Use the pasture pipette to mix both layers together. Then you will place the bottom layer, the organic layer, into a small Erlenmeyer flask. You will repeat this procedure 2 more times. After extraction, we will use sodium sulfate to dry the solution. This will require a significant amount of sodium sulfate because water was a primary component in the experiment. Once it is free-flowing, we can place the methylene chloride in a clean conical vial. Before doing so, we want to weigh the conical vial without any product in it so that we can calculate the mass of the product later. The product is added to the vial, and the remaining desiccant in the Erlenmeyer flask is disposed of in the desiccant waste. Before evaporating the methylene chloride, we'll dispose of the water bicarb solution in the unwanted aqueous material container. Don't forget to remove your spin bar before emptying the Erlenmeyer flask. Now we'll evaporate the methylene chloride with a gentle stream of air. This may take several minutes. You will most likely be left with only a few drops of cinnamaldehyde. Then we will weigh the conical vial with product. Take the difference between this weight and the weight of the conical vial only to obtain the weight of the material recovered. To characterize the compound, we will acquire an IR using the capillary film technique. Use an open capillary tube to obtain a few drops of the product and slightly tap it on one of the salt plates. Then place both salt plates together. Try to have your product right at the center of the salt plates for best results. Place the salt plates on the salt plate container in the IR machine. Then run the IR and find the peaks. Here we have the carbonyl peak, the C-to-C double bond peak, the 4 benzene ring peaks, and then the aldehyde peaks.